Great feedback. Then on Sunday I got the email that both Andy Fabi and Matthias Roskowski couldn't be here, so I tried to impersonate them. I will miserably fail, of course, and give some introduction to the radio mode theory before I then go in the second part and talk about cosmic ray feedback. So, to set the stage here, so we haven't really talked about galaxy clusters so far. There are two types of galaxy clusters, cool cores and non-cool core clusters. The cool core clusters usually show signs of radioactivity, and if you have a well-resolved X-ray image, you typically see these bubble-like features of a recent outburst and a more sort of an older outburst in the Perseus galaxy cluster. So that led over the last 10-ish years to the paradigm that supermassive black holes co-evolve that they're hosting CD galaxies at the centers of galaxy clusters. Under certain circumstances, they can launch relativistic jets that blow bubbles, so X-ray cavities, filled usually with radio emission. And in the outer cavities, sometimes you see actually low frequency radio emission, indicating an aged radio population in there. And potentially, that's at least the standard law, they are able to provide energetic feedback back to balanced cooling. What are the key points that we have to understand here? First of all, the energy source. It's most likely associated with the release of non-gravitational energy due to the accretion onto this black hole, or possibly its spin. In the second part, once this jet basically went and blew bubbles, it's of course important to understand the jet-ICM interaction and the rising of those bubbles. And interesting topics include magnetic draping, cosmic ray confinement, entrainment of the ICM plasma into the jet, and of course the duty cycle. I will touch upon part of those issues later on. And finally, we want to understand the heating mechanism. So in fact, I tried to go beyond the thermal bomb model that we heard this morning. A few interesting things that heating mechanism has to obey to sort of be in accordance with the observations. First of all, it has to be self-regulated to avoid overcooling. And we have seen this morning by these nice simulations by Pfrommer what happens if you do not have some heating mechanism in the center. It just overcool badly and form 10 times too many stars. Second, the heating mechanism has to be thermally stable to explain the temperature floor in the hot gas that sits roughly around 1 kV or 2 kV, so it depends on the cluster. And finally, the heating mechanism has to have a low energy coupling efficiency. What do I mean by this? First of all, the gravitational binding energy, as we heard this morning, is m sigma squared. And from the m sigma relation, we know that the black hole mass is related to the mass by 500 or so. So the available black hole energy to be extracted is the radiative efficiency, 10%, of the rest mass energy of the black hole. If you combine those two, you find that the energy relative to the gravitational energy is 0.1 times the ratio of the masses times the c over sigma squared. So that means we have in principle 200 times the energy available for feeding back. So there's no energy problem here. More than enough energy available. So what happens now? The relativistic jets, and we can see this in highly resolved radio images, displace the intracluster medium at the location of the cavities. That means they do PDV work against the ambient intracluster medium, as well as supply internal energy to the cavities. So we all know from the thermodynamics that the total energy required to create a cavity equals its enthalpy. So it's the internal energy plus PV. So that's just a formula. If you write this down, so that basically means you have the gamma factor of the medium internal to the bubbles over gamma minus 1 times PV, which results to 4 PV, assuming we have a relativistic filling. Well, we observe radio emission, so that's not too bad of an approximation. However, only 1 PV is directly available for mechanical work on the surroundings because the 3 PV is stored in internal energy. So if you now plug in typical numbers, what is the work that can be done by the two bubbles in one outburst? So basically, you have a typical bubble radius of 20 kiloparsecs. That is being blown in an ICM of typically the density of 10 to the minus 2. And temperatures are 3 kV, so they can immediately infer that the work that can be done is 10 to the 59 ergs. So where does this energy go? Well, the energy release time is of order the sound crossing time of these bubbles. And if you work this out, it turns out this is very similar to the point rise time or to the refill time of the displaced bubble volume. Of course, the radial dependencies of the three time scales is different, but all of those give roughly indicated time scale of 3 times 10 to the 7 years. So that means we have an AGN heating rate, which is just this PV, divided by the point rise time, so 10 to the 59 ergs divided by 10 to the 15 seconds, which gives us 10 to the 44 ergs per second for this one outburst, which miraculously is of order the observed X-ray luminosity of those cores.
Sorry, you suddenly put that word heating rate. We haven't explained how you heat.
You're absolutely right. I just, at the moment, I'm doing a thermodynamic statement. I haven't actually told you what heats. Absolutely true. So, in principle, that's a necessary condition. By the way, it's not a sufficient condition because, of course, we have to couple this. So, this shows that the necessary condition for balancing the X-ray cooling losses and increasing the ambient core entropy is available. And in the following, I define now what the X-ray people do, entropic function. So that means this is a constant upon adiabatic processes. So it's simply the temperature divided by the density to 2/3. And let's simply correlate how the enthalpy correlates with the entropy that you measure in the core. So the x-axis, that's the entropy measured from the X-ray images. On the y-axis, you can see the cavity enthalpy. And the different colors indicate different different temperatures of the cluster. Clearly, there is a correlation. So the more enthalpy a bubble has, the more apparently the higher the ambient entropy is. It's a correlation. It may not be a causality argument. And most importantly, if you compute the binding energy of the entire core radius, so with an R2500, you can see that the most luminous outbursts here have an energy that is larger than the binding energy of the gas in that halo. Meaning, energetically, it could completely blast the gas away and unbind this gas from the core. Now, I also told you clusters come in two species, cool cores and non-cool cores. In fact, the maximum entropy of cool core clusters is over here. So, while observationally the bubble enthalpy is coupled to the entropy, AGNs cannot transform those cool cores to non-cool core clusters that have maximum entropies of 600 kV centimeters squared. So clearly it regulates those cool core clusters, at least on the buoyancy time scale, that AGNs apparently do not transform cool core into non-cool core clusters. That's an important ingredient here. Now, from global cluster thermodynamics, and actually to do exactly what is suggested, let's go and look at the physics. What happens now to a bubble that rises in the ambient cluster medium? So of course we all know that the cluster medium is magnetized. It's weakly magnetized, so the magnetic energy density is only about 1% of the thermal energy density, but that is enough to actually completely change the dynamics here. So what I'm now talking about is very general. It applies to any object that moves superalphanically through some ambient magnetized medium. So in this context you can think of this as a bubble, but it could also be some cloud in a hot wind, it could be a star that sort of moves through the galaxy, etc. So what happens now is, as this object moves through the ambient medium, magnetic field is straight along the interface, and what you see here in color is the magnetic energy density. And if I now show you basically this movie and a few magnetic field lines, you can see
here, go here, magnetic fields perpendicular to the direction of gravity.
Absolutely, absolutely. So you can see that as the body moves, magnetic field lines are draped at the interface, and you soon reach a steady state that's characterized such that the rate of field lines that this body is sweeping up equals the amount of lines that that leave this draping layer there. Most importantly, the steady state is characterized by a strongly magnetized sheath with an energy density that equals the Ram pressure. And that's a simple MHD effect that is very difficult to circumvent. What does this imply now for our rising AGN bubbles in a cluster? Well, by the way, first of all, what is magnetic draping? One question I often get is magnetic draping similar to Ram pressure compression? And the answer is no. There's no density enhancement for magnetic draping. So in this case, we simulated a heavy bubble, but the same applies to a light bubble. And you can see that at the interface, there's a slight density blip rather than an increase at the position where this strongly magnetized sheath falls. And the reason for this is basically you can also see the same effect if you do an analytic solution for magnetic draping in an incompressible flow, or if you run an ideal MHD simulation, which I have done on the previous slide. So why is it that you actually now increase the magnetic field strength? That's very simple to understand. Magnetic flux is still frozen into the plasma, but the plasma here is pulled into the direction of the field lines, while the field lines get stuck here, and because you move the field lines closer together, that means you increase the magnetic energy density, and that's the explanation of magnetic draping.
If the magnetic field in which you are moving is turbulent because it's a very low...
I'm coming to this.
Why not conservation effect that?
Absolutely. I'm coming to this basically in a few slides. For the moment, let's assume we have a coherence length that is large enough for magnetic fields to get draped. We realized this, and then a few years back, Mateusz Ruskowski ran a couple of simulations. So the time sequence goes from the bottom to the top. On the left, you see the non-draping case. On the right, a draping case. So it means a coherent field on a large enough length scale for it to be draped. This shows the log of the density, and clearly the bubble stays coherent, whereas in the pure hydro case, the bubble, after rising a scale height, starts to be disrupted by buoyancy instabilities. This is the log of the magnetic energy density, and you can see here, you can barely see the effect of the bubble on the surroundings, whereas here you can clearly see this draping feature in these light bubbles. And finally, if you now sort of produce an X-ray mock image of such a situation, on the left-hand side you can see the bubble being disrupted, unlike what you observe in the X-rays, whereas on the right-hand side you still see a coherent figure because the magnetic tension suppresses the Kelvin-Helmholtz instability that would otherwise disrupt those bubbles. So now, answering the question from Montessier, what are the conditions for magnetic draping? First, the ambient plasma needs to be sufficiently ionized that we have magnetic flux freezing, so that's not a problem in a galaxy cluster. Second, we need super-alphinic motions of a cloud through a weakly magnetized plasma. That means the alphinic Mach number needs to be larger than 1. And the alphinic Mach number, for those of you that only sort of, or usually don't work with magnetized fluids, is the plasma beta factor, is the ratio of thermal to magnetic energy density times gamma, 5/3, times the sonic Mach number squared. And finally, the most important condition for draping to occur is that the magnetic field needs to be coherent across sort of a cylinder aligned with a stagnation line that impacts those bubbles. So that means the ratio of magnetic coherence over the curvature radius of the working surface needs to be larger than 1 over the alphinic Mach number, which is typically, for typical conditions of a cluster, 0.1. So that means if you have a bubble of radius 20 kiloparsecs, you need to be coherent on a scale of about 4 kiloparsecs. Alright? And that's, at least for the clusters we studied so far, in Hydra A, this seems to be the case because there's a lower limit by deep projecting Fourier rotation maps of 10 kiloparsecs. So that leaves us with the open questions that we hopefully try to answer this afternoon. First one, how is then the accretion output thermalized? And there's different possibilities: dissipation of waves, turbulence, releasing potential energy, thermal conduction, cosmic ray heating. The second open question, is the heating-cooling balance actually thermally stable? Turns out that's not the case for turbulent dissipation and conduction, as we'll show that is the case for the cosmic ray heating mechanism. And finally, how is the accretion rate tuned? The problem we were facing is that the cooling radius, 30 kiloparsecs, is about 10 to the 8 times the Schwarzschild radius of those black holes, using a black hole of 5 times 10 to the 9 solar masses. So apparently over this huge range of scales, the feedback operates, and I think these are important questions that we hopefully touch upon this afternoon or tomorrow. Let me now come to the second part of one possibility how heating could occur. And just to introduce cosmic rays, that's one of the most impressive power laws that we have discovered so far in astrophysics. So it's a power law momentum spectrum with 33 decades in flux and about 12 decades in energy. It's pretty power law-like, at least up to 10 to the 15 EV. And we believe that diffusive shock acceleration of cosmic rays at supernova remnants is the cause of that power law. So you can basically work out what is the pressure contained in cosmic rays that you observe there. It turns out that is equal to the pressure in magnetic fields and turbulence in the interstellar gas at our position. Now what we do not know is what is the cosmic ray pressure in cluster cores, and second, what is then the dynamic impact of cosmic rays on the cooling gas and star formation in ellipticals. And I try to shed light on those questions now in the following. First of all, how do cosmic rays interact with the gas? First of all, the mean free path is very long, so they cannot directly interact by collisions. But cosmic rays scatter in magnetic fields. That causes the cosmic ray momentum to be isotropized. And there's a cosmic ray streaming instability found by Calfan and Pierce in '69 that goes as follows. If the cosmic ray that gyrates around a magnetic field has a velocity that is larger than the wave velocity, it excites alphane waves, so wiggles in the magnetic field. And the cosmic rays gyrates these waves on the scale of its Lama radius, or gyro radius. So that means it can now scatter off those waves, which limits the cosmic ray's bulk speed to much below the intrinsic speed, which is the light speed. So the damping of those waves now transfers the cosmic ray energy and its momentum to the thermal gas. So this ingenious idea now provides a means for cosmic rays to exert a pressure on the thermal gas by means of scattering off those alphane wave field and to heat the surrounding gas. And potentially this may be able to heat cool cores. And there's a very nice paper in Löwenstein that pointed out a lot of the things we talk about today. But when I read this, I was very surprised because people have not really appreciated this paper, I think, in the past. At least not as much as what, they talk about self-regulated AGN feedback, etc. Moving on. So how do cosmic rays now move in the interstellar or intracluster medium? The total cosmic ray velocity is the sum of the advective gas velocity, the streaming velocity, and the diffusion velocity. What I mean by those two? Cosmic rays stream down their own pressure gradient relative to the gas, and the streaming velocity is simply given by scattering off this wave field, so they stream with the alphane speed and basically in the opposite direction of their pressure gradient. And relative now to this wave field, cosmic rays diffuse in this wave frame due to pitch angle scattering by MHD waves. And of course, both processes are transports along the local direction of the magnetic field. And that means the streaming velocity is simply the negative diffusivity times the pressure gradient, known as pressure gradient. So if you now work out the energy equations, that's what we want. So this is the conservation of thermal and kinetic energy on the left-hand side. And what are the sources? The sources are basically associated with the cosmic ray streaming. You can also derive a cosmic ray energy equation which basically tells you that the cosmic ray energy is conserved apart from the two loss mechanisms. The first being, if cosmic rays scatter off this alphane wave field, they do PDV work on it, so they adiabatically sort of push the balls outwards, and that means they lose energy adiabatically. That's the first term. And of course this energy is a source term for the thermal energy. And second, that's the alphane losses basically because it takes them energy to basically transfer their energy to the Alfvén wave field. Now, I thought I should take this radio mode actually more literal than just, there's radio emission, that's why the AGN heats. So the expectation was, by looking at M87, that this is a radio image of M87 by VLA, and if the expectation was if you look at this AGN at low frequencies, you're sensitive to the fossil electrons. You're sensitive to time-integrated activity of AGN feedback. It turns out LOFAR observed this AGN and the image looks identical. Right? So the halo, that you see here, is confined to the same region at all frequencies, and there's no low frequency spectral steepening visible. So there appears to be a puzzle of these missing fossil electrons. Where are those? That have been injected in the past by this AGN and have longer cooling times. One solution is that we're living in a special time. M87 turned on 40 million years ago. This, of course, conflicts the order unity duty cycles and inferred from statistical AGN studies. And the second solution is a very nice physical solution. So this is the electron cooling time as a function of electron momentum. And you can see that there's one branch, this is synchrotron cooling. The larger the magnetic fields, the faster the electrons cool. On the low energy side, there's Coulomb cooling. The denser the gas, the more collisions the electrons have, the faster they cool. And in fact, there's a maximum cooling time, there's a bottleneck, and you basically need to move this bottleneck down to 40 million years. This is what we infer for the radio halo age. And that means only if you mix the fossil electrons efficiently with the dense cluster gas surrounding M87, you can remove those and move those electrons to the thermal pool. So this, of course, now also implies efficient mixing of the protons that provide the pressure of those bubbles. And this predicts gamma ray emission through the proton-proton interaction, making a neutral pion and causing the emission of 2 gamma rays for each interaction. Now let's look at the multi-frequency picture of M87. In fact, this is radio, optical, X-ray, gamma rays. There's a high state associated with the jet emission that is variable, and a low state. It has a steady flux, there's no variability visible in M87, and the spectral index that I show here is consistent with the proton index in this picture, and turns out this is the same index that you also see in the center by LOFAR. That means it's the cosmic electron injection index. So those are injected by the same process. And finally, of course, if that emission would be spatially extended, that would be a smoking gun to see the first gamma ray signal from a galaxy cluster. So people are currently working on sort of showing this. Nevertheless, what we can do now, we can basically use X-ray data to assume a density and temperature, or to measure a temperature and density profile. We assume a constant relative pressure ratio of cosmic ray to thermal pressure. This is also needed for self-consistency requirements. And this means we can basically estimate the amount of cosmic rays that are needed to provide or to basically power this observed gamma ray flux. And it turns out you only need 30% of cosmic rays relative to thermal gas to explain this gamma ray emission. So this is an agreement with the non-thermal pressure constraints from dynamical potential estimates made by Churasov. Now, we have measured all ingredients. Let me now sort of phrase this up. We have a cosmic ray Alfvén wave heating term that is proportional to the Alfvén speed times the cosmic ray pressure gradient. We can obtain the Alfvén velocity by minimum energy arguments made by LOFAR and using the densities that are measured in the X-rays. We calibrate this pressure ratio of cosmic rays to the gamma ray emission, and we use the X-ray data to infer the thermal pressure profile. And this is not that important, but we assume that there are some pressure fluctuations that you also see in the X-ray images that is caused by weak shocks of Mach numbers 1.1. So that means we can actually pinpoint down the heating rate as a function of radius from observations only. There's no free parameter. And of course, we measure the radiative cooling by observing the X-rays. It's simply proportional to the density squared times the cooling function. That depends on metallicity and temperature. So we have all the ingredients available. Now let's plot both of them as a function of radius. And red is heating, blue is cooling, and that's what I found. So apparently, the heating matches the cooling at every radius up to the radial extent of the radio halo. So we appear to have global thermodynamic equilibrium in M87 today, given the amount of observed gamma rays. Now, only one point. So of course, global stability does not imply local stability. If you perturb now that point, which would be in equilibrium, and assume that we have isobaric perturbations to the global thermal equilibrium and that cosmic rays are adiabatically trapped, you basically have several points. On the right-hand side, this is an unstable fixed point. If you perturb it, either heating or cooling wins. On the left-hand side, you have a stable fixed point, and you can see that depending on whether you're on the left or right-hand side of the separatrix, you're either locally stable or locally unstable. Now I did this and found that for the observed temperature range in Virgo, we have local instability up to 1 kV, where an island of stability is emerging. In fact, that's basically given by the location of the iron shell complex. And just at 1 kV, this heating mechanism is supposed to be thermally stable. And that's the observed temperature profile in Virgo, which levels off at 1 kV. Right? So it's either too good to be true or it has something to do with reality. Anyway, I leave it with this. And just one last word on thermal conduction. Cosmic ray heating dominates over thermal conduction by at least a factor of 2 to 4 in the entire range of the radio halo. And it also predicts that we actually should observe the similarly produced hadronic radio emission at high frequency. So that's one possibility to actually show that this mechanism in fact works. I leave my conclusions and basically try to emphasize that the LOFA puzzle of missing fossil elements is solved by mixing those with a dense cluster gas. Then the predicted gamma rays identified with the low state of M87, and given those two ingredients, I can basically derive an observationally calibrated alpha wave feeding rate that turns out to be to balance radiative cooling losses on all scales. And the local thermal stability analysis predicts that predicts an observed temperature floor at 1 kV. Thanks very much.
In the back there.
So, I'm really interested by this. You talked about hadronic emission. I mean, in order for this to work for Virgo, are there enough, if there were enough if the cosmic ray energy density was high enough to be to do this in Virgo, to keep the temperature floor,
yes,
would you see it in the gamma rays? I mean
that's...
should one in principle see it? I couldn't read it off that line.
Yes, that's basically what I did, right? I mean, that's the observed gamma ray emission in M87. And that emission is basically what I identify as the gamma ray emission because of hadronic proton-proton collisions in the core of Virgo. Now, of course, M87 is the closest AGN interacting with the cluster gas. So if you would do the same in Perseus, unfortunately there, the jet emission, which is blue here, is much higher and dominates the total emission below 200 GeV or so. And we have not yet found actually any emission below, but we are not that sensitive yet because Virgo is 5 times further away than Perseus is 5 times further away than Virgo. Yes.
No.
Your stability analysis, you assumed isochoric cooling? You had a fixed density profile, or was it for isobaric cooling?
I assumed isobaric perturbations.
Okay.
Locally I assumed global stability, and then I perturbed the stability around, and I assumed isobaric perturbations.
How does the heating rate scale with the density?
Well, it scales with the density gradient, if you want. If the temperature is basically right. I mean, basically, it's the cosmic ray pressure gradient that enters there. Now, depending on how the cosmic ray pressure relates to the thermal pressure, which I think is the same. That's what I assumed here. That's basically what went in here.
Okay.
So it's density.
Isobaric is almost never stable. That's why I'm surprised.
So in this case, it is.
Frank?
So the idea of the magnetic draping to keep your bubble stable,
Yes.
you require that these magnetic field lines run perpendicular to the direction of gravity, which is fine in the core, but as soon as you go, where the temperature starts to go up radially, you get a magnetothermal instability, and your magnetic fields will align themselves
Well,
in
the
the radial direction.
That's not true. You get the magnetothermal instability just outside the core when the magnetic temperature profile drops.
Right.
Inside, when you basically have a
Inside
rise.
you're fine, but that means that when your bubble goes up, you wouldn't predict that with this picture,
Yes.
the bubble should burst open right at the radius where the temperature
Well,
profile
in
starts to
fact,
increase. Right?
in Virgo, this maximum temperature profile is at 200 kiloparsecs. So we're talking about 35 kiloparsecs center. So that if the bubbles always make it all the way up there, then that's true. But I think right now they're being shredded, and that's very interesting. I think I don't know for sure what is the cause of this, but potentially one of those conditions was not actually fulfilled. So maybe it was sufficiently tangled in this direction that it was disrupted, or maybe there was something else that perturbed it such that it is being disrupted right now. I mean, you see this, right? I mean, you see this very nice plume here. You can clearly see the bubble being disrupted as we speak, right? So this is a clear sort of really tailored plume that you see.
Okay, I'm
This-
sorry. I think we should move on. Save those questions and comments for the discussion, please. Thank you very much, Chris.